Alright, hello everybody and welcome to a new lesson from this chapter, which is a fundamental problem for recursion and also for divide and conquer. As I've said, they are very related to each other. And the problem is that we are given two positive integers a and n, and we need to compute the value of a to the power of n. So, for example here, if a equals 2 and n equals 10, the output is 1024, right? Because 2 at power 10, you can compute it, it is 1024. And that's it. As simple as that, straightforward. As usual, let's start with a brute force approach. And for a brute force approach, we can do like the first thing that comes to mind. And that is obviously, like in this example, let's say, what's 2 at power 10? Is actually 2, crossed another 2, crossed another 2, crossed, and so on and so forth, crossed another 2, right? And we do this for 10 times. Yep. And that's it. A at power n is, of course, a, crossed, dot, 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 and so on and so forth, crossed a. And we do this, of course, n times, right? So we are going to need to multiply a to the product for n times, right? So obviously it's a repetitive thing. It depends on the value of n. So we are going to need a repetitive loop for that. And that loop could be as simple as a for loop. So I can have my answer. Let's say I store my answer in a variable, right? And the answer starts with 1. And then what I can do is that for each value of I, right, from 0 all the way to n minus 1, or from 1 all the way to n, doesn't really matter. All that's important is that we make exactly n steps here. We can just multiply the answer by a, right? And at the end, we are going to have our answer, which we will return. So, straightforward, very simple, right? The time complexity is also pretty straightforward. As you can see, these are constants, right? Constant, right? Constant operation is a multiplication. And we have to ask ourselves, how many times do we do this multiplication? How many iterations does the for loop make? And of course, it goes with I through every value from 0 to n minus 1. 0, 1, 2, dot, 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 n minus 1. So this is a total of n steps. This algorithm has, in conclusion, a time complexity of big O of n. Alright, perfect. Not bad. This was simple. But the thing with that problem, with this problem, logarithmic exponentiation, is to be able to do this quickly for large values of n. So for something like n equals 10 or n equals 1000, yeah, you can do that obviously and it's going to work. But what about this type of constraints? A and n are positive integers which are, I don't know, less than or equal to 10 at power 9, right? For this kind of scenarios, obviously 10 to power 9 iterations is not pretty quick, right? So the thing with this problem is that, first of all, you are going to see this a lot when dealing with formulas. For example, you have to come up with the formula for combinations, which uses something like that, or just a simple mathematical formula for a to the power of n. And when you have this type of constraints, we need a better approach than the linear one. And also, as you might have noticed, when a and n are 10 to the power of 9 each, the value of a to the power of n is huge. So we also won't be able to just store it in a int or long or something like that data type. And yeah, this is why this problem is like given in the context of when the values are so huge, it asks you to basically compute the value of a to the power of n modulo something, right? So you are given basically 3 integers in the input. They are a, n, and some other integer modulo, because a to the power of n exceeds any data type out there, but a to the power of n modulo something, which is, let's say, less than or equal to 10 to the power 9 or something like that, will not exceed it, right? So it's not something super important. It doesn't affect the way of thinking, but it's just there to like be able to return like a very decent data type, right? So don't worry about the modulo. We are going to take into account, but as I've said, it's not a big deal. For example, here in the brute force approach, what should I have done? I start with answer equals 1, and then for each of the n steps, instead of just doing answer crossed equals a, so just multiplying it by a, I can do something like this. Answer is equal to answer crossed a, right? And all of that modulo mod. And this is it, right? So each time you multiply the answer by a, also add the modulo mod to make sure that the answer is always keeping or storing the remainder of all those products modulo mod, and then return answer, and that's it. So let's see how we can use recursion and divide and conquer to approach this problem in a way quicker manner than big O of n. Alright guys, all we need to do here is use a simple but powerful mathematical property. Let's take 2 to the power 10 of our example, right? 2 to the power 10. We can write it, of course, as 2 to the power 10, as it is. But can we write it in some way that is still a power, right? But with a less exponent? Yes, we can. 2 to the power 10 can be written as 2 to the power 5, everything at power 2. So, if I am able to first compute this 2 to the power 5 and know its value, let's call it x, then all I have to do is multiply x by itself and I have the answer to the problem. So as you can see, from 2 to the power 10, now my job is to compute 2 to the power 5. Okay, can we write 2 to the power 5 as another power, but with a less exponent? Unfortunately, we can't, right? I could with 2 to the power 10, because 10 is not a prime number, so it has at least one pair of divisors, which multiplied together give us 10, and those are 5 and 2. So I can write 2 to the power 10 as 2 to the power 5, everything at power 2. Now with 2 to the power 5, because 5 is a prime number, I can't do that. But I can do other thing. I can write it as 2 crossed 2 to the power 4. So now, if I am able to compute this 2 to the power 4, let's call it y, all I have to do afterwards is just multiply y by 2, and I have the answer to my problem. Now, we have to compute 2 to the power 2. This time, 4 is not a prime number anymore. It is even, so I can write it as 2 to the power 2, everything at power 2. So if I'm able to compute this 2 to the power 2, which I call z, all I have to do is multiply z by itself, and I get the answer to the problem. Now all I need to do is compute 2 to the power 2. 2 to the power 2, obviously, we don't need to write it as anything else anymore, because it's just 2 cross 2, which is 4, right? So see what I did here? I said that in order to compute 2 to the power 10, I first need 2 to the power 5. To compute 2 to the power 5, I first need 2 to the power 4. To compute 2 to the power 4, I first need 2 to the power 2. To compute 2 to the power 2, I first need the value of 2, which I already know. It's a power of 1, right? So it's already a number. And now I can go back and say, all right, I have compute 2 to the power 2, which is my z, right? Having computed my z, which is 4, I multiply 4 by 4, and I get a 16. So now I know the exact value of 2 to the power 4. I go back here, and I can say that y is equal to 16. I have to multiply 16 by 2, and I have 32. I know the value 2 to the power of 5. Now I can compute the value of 2 to the power 10, because I just have to multiply 32 by itself. 32 cross 32 gives us the answer to the problem, which is 1024. So, why do I do this? Why did I do all of that, right? Because as you can see, at each step, our problem becomes to compute a at some power which is smaller than n. Here, n was 10. On the next step, n was 5. On the next step, n was 4. On the next step, n was 2. So as you can see here from 10, because it is an even number and I can write it as 5 cross 2, n became 5. The next problem or sub-problem was to compute 2 to the power 5. This is unfortunately not even, so the next sub-problem would be to compute 2 to the power 4, which is even, so the next problem would be to compute 2 to the power 2, which obviously the next problem is compute, let's say 2 to the power 1, which I already know. So as you can see, instead of starting from 2 to the power 0, like in the brute force approach, and from 2 to the power 0, multiply by 2, compute 2 to the power 1, multiply by 2, compute 2 to the power 2, and do this until I compute 2 to the power 10. Instead of doing this 10 iterations, just increasing the exponent by 1 every time, I found out a smarter approach in which I sometimes even divide the exponent by 2, or decrease it by 1, or divide it by 2, or decrease it by 1. So if I had here 10 iterations, right? Here I have only 1, 2, 3, 4 of them. Now, again, I know this might not be very impressive with such a small example, but in fact it is. Because when n is even, n gets divided by 2. Then if it's odd, only decreased, but then it would be even again, and it would get divided by 2 again, and so on and so forth. Let's take a greater example. Let's see, I had to compute 2 to the power 100, for example, right? 2 to the power 100, actually, sorry about this, let me write it here. Alright, let's say I had to compute 2 to the power 100, right? Our brute force approach makes 100 steps, 100 product operations. But my approach would say something like this. To compute 2 to the power 100, I first need to compute 2 to the power 50. And then just multiply it by itself. To compute 2 to the power of 50, I first need to compute 2 to the power 25, right? Because 50 is even. So I can write it like that. In order to compute 2 to the power 25, 25 unfortunately is not even, so I can do the trick above. But what I can do is make it to write it as another power of 2 which has an even exponent, to say it like this, right? So to compute 2 to the power 25, I need to compute 2 to the power 24 and multiply that by 2. Now, 24 is indeed even, so I can one more time say that I need to compute a power which has the exponent half the original one, and 2 to the power 12, same spiel here, is 2 to the power 6 to the power of 2, 2 to the power 6 is 2 to the power 3 to the power of 2, and 2 to the power 3, we have 2 more steps, so don't worry about it, is 2 cross 2 to the power 2, and 2 to the power 2 is indeed 2 crossed 2. So let's see how was the evolution of my exponent for 100. From 100, I jumped straight to 50, then I jumped straight to 25, then I had to jump to 24, but then I jumped straight to 12, to 6, to 3, and then 2, right? So see how many times I actually divided by that exponent by 2. A lot of times, right? I have 1, 2, 3, 4, 5, 6, 7, 8. I only do 8 steps compared to the 100 steps that my brute force approach did. So this is super powerful. All we need to do is just make a recursive algorithm, which, as you can see, is actually based on divide and conquer. Don't worry if you don't know yet divide and conquer, that's completely cool. But what divide and conquer says is that when you have to solve a bigger problem, start by solving smaller problems of the same type and combine them together. And that's what we do. In order to solve the bigger problem, 2 at power 100, let's start by solving 2 at power 50 and then multiply it by itself. For solving 2 at power 50, let's start by solving a smaller and even smaller subproblem, 2 at power 25, and so on and so forth. So, the thing here, on a more general note, I think we've seen a lot of particular examples, is that a to the power of n can be written in one of two possible ways. The first way is a to the power of n divided by 2, everything to the power of 2. Obviously, this is possible only if n is even. So if n is even, or the other scenario is when n is odd, obviously, in which we can't do that, right? And because we don't know or we can't find very quickly like some pair of divisors for n, we are not going to do that. We are just going to write it as a to the power of a crossed a to the power of n minus 1, right? So what you basically see here is a way of writing a to the power of n in a recursive manner. This is a recursion formula, right? A to the power of n is written or expressed in terms of other numbers, powers of the same type. A to the power of n divided by 2 squared if n is even, or a to the power of n minus 1 crossed a if n is odd. So let's see together how can we write a recursive function in order to compute a to the power of n using this formula. Okay, and here is the algorithm. So let's say we make a function which is called pow and has these two arguments, a and n. And this function will return for us a to the power of n modulo mod, right? Perfect. Now, as any other recursive function, we first need to think about the stopping point, right? We have to make sure that the function doesn't call itself an infinite number of times. So for that, we have to make sure we set a stopping point. And the stopping point could be n equals 1, right? Because for n equals 1, we obviously need that the value of a to the power of 1 is a. So when n equals 1, I can just return a modulo mod, alright? Be again careful because a might be greater than mod, so also make sure that you make this modulo mod. Now, otherwise, so if I ended up here, this means that n is greater than 1, right? Because otherwise I would have exited the function with this return. If n is greater than 1 and n is even, then I have something like a to the power of 2 crossed k, right? I can write n as 2 crossed k, which is of course a to the power of k, everything crossed 2. At power 2 squared, right? So what I do is that I compute this a to the power of k in a variable x. So x is equal to, and how will I do this? Of course, using the function, because that's what the function does. So I compute a to the power of n divided by 2 and store it in a variable x. And the only thing I have to do is return x crossed x, everything again modulo mod. Now, if I am here, so obviously n is greater than 1 and it is odd, what will I do here is only write a to the power of n, as I've said, as a crossed a to the power of n minus 1. A to the power of n minus 1, of course, will be computed using the function. So I'm going to call power of a and n minus 1 multiplied by a and everything modulo mod. Awesome. Now this is our algorithm. Let's see what is the time complexity of it. Well, to come up with the time complexity, we have to think about how the function calls look like, right? So obviously, when I'm going to receive in the input the integers a and n, the only thing that I have to do to solve the problem after I have implemented the function pow is just to return pow of a and n, right? That's what I need to do in the main algorithm. Now, when I call this pow of a and n, this is going to result in another function call if n is greater than 1, right? Either a and n divided by 2 or a and n minus 1, depending on n's parity, right? Let's take actually another example again, because I can show you better with this. So let's take an example. Let me think about one. I think we can take 66 as an example. So let's say we want to compute, I don't know, 2 to the power 66, right? So the first function call is obviously pow of 2 and 66. Now, because this is even, right, we are going to write it as 2 to the power 33, everything squared, right? So the next function call will be here in order to get the value of x, and will be pow of 2 and 33. Pow of 2 and 33. Now 33 is odd, and inside this function call, I return this instead, and I say that it's a crossed pow of a and n minus 1, right? So the next function call is actually pow of, I'll just write the pair, 2 and 32. Then, in this function call, the next function call, because 32 is even, is 2 and 16. The next function call 2 and 8, and you got the idea. So, my point here is that we obviously see, and we've talked about this, that this second argument, the n, sometimes gets divided by 2, sometimes gets decreased. Sometimes divided by 2, sometimes gets decreased, until it reaches the value of 1, in which we just return this. As you can see, we only return a modulo mod. We don't call the function again. So that's the stopping point, right? So we need to ask ourselves this. How many function calls do we do at most until we hit the stopping point? So we start from some value of n, and we are going to do the next and the next and the next function calls until we reach the last one with n equals 1. Well, in the worst case scenario, here is what happens. If n is odd, so we have a function call, let's say pow, right? We call pow of a and n is odd. Then what we know for sure is that the next function call will be for a and n minus 1. Am I right? And because n was odd, now n minus 1 will be for sure even. And what does this mean? Because n minus 1 is even, the next function call will be a and n minus 1 divided by 2, which we don't know if it is odd or even, but doesn't matter, because starting from the exponent n with at most two function calls, I reached something which is less than or equal to n divided by 2. Actually, I think it's strictly less, but doesn't matter. So, all I do is that when n is odd, call the function basically 2 times n minus 1 divided by 2, and I already made n half of what it was 2 calls earlier. And the best case scenario is, of course, when we call the function pow of a and n at some point, and n is even, and directly on the next function call, what will happen is that n will get divided by 2. So, either after one function call or after 2 function calls, I reach a value of n, I reach an exponent which is less than or equal than n divided by 2, right? So, think about it this way. Let's say we have an example, right? An input, such that n being odd is occurring very often, right? So, we have the first function call here. N is odd. So, I need to make 2 other function calls until from n I reached something less than or equal to n divided by 2. Then let's say again that this n here inside this function call, I don't know its value, but let's suppose this is also odd, right? I have to make one function call, and now it is even because it got decreased by 1, and I make another function call, and now this even n got actually also divided by 2. So after 2 other function calls, I have an n which is less than or equal to n divided by 4. Let's suppose again, I don't know the value of n in this function call, but let's suppose it is odd. So I'll do one more function call with that value minus 1, and that value minus 1 is now even, so one other function call, and we end up here, having the exponent, the second argument, n being half of what it was here. So, being half of what it was here, right? So, if I had some exponent here less than or equal to n divided by 4, got decreased by 1, and now got divided. So, it will be for sure less than or equal to n divided by 8. And so on and so forth. Until obviously I reach the point where I call the function with n equals 1, right? With some a and 1. So the real question is, for how many times could have I possibly called this function until from the value that it started with, n, the exponent got to be equal to 1? Well, as you can see, what I do after each 2 calls at most is divide n by 2. How many times am I able to divide the number n by 2 until it eventually equals 1? This is a mathematical formula, this is a mathematical definition actually, and is called the logarithm, right? So the logarithm of n, log of n, tells us how many times you can divide a number by 2 and obviously keep its integer part until it has value 1. And because we divide each exponent by 2 after at most 2 function calls, we are going to need at most 2 crossed log n function calls for it to reach 1. So, in conclusion, our algorithm calls the pow function at most 2 crossed log n times. And what do we do inside the pow function? Well, we have an if statement. If n equals 1, which is constant, we return a modulo mod, which is constant, another if statement, which is constant. We call another function. We don't care about that because obviously this pow is another function call. We just want to look what we do inside one specific function call, not the other ones. We make basically an assignment after we know this value. Then we return x crossed x modulo mod, This is constant. And then here, again, we don't care about this one because it's a different function call. We make this, we multiply a by that number once we have it. And again, get the remainder of the expression modulo mod. So as you can see, in each different function call, we make only constant operations. So the total time complexity of the algorithm is how many function calls do I have at most crossed the time complexity of each function call. What happens inside each function call, which is, as we've said, only constant operations big O of 1. So we have a total of 2 crossed log n, drop the constants for time complexity, and we can say that our algorithm has a final time complexity of big O of log n. All right. So what I want you to remember is when dealing with recursive functions and computing the time complexity of them, be careful to count how many different function calls will we have in total at most, and also what does a function do inside it, right? Because if inside the pow function I would have had, let's say, a for I equals 1 as long as it's less than or equal to n I++, that for would be big O of n. So inside each function call, I would have had n iterations. So it wouldn't have been only 2 crossed log n. It would also been crossed big O of n. And I had big O of n log n time complexity I would have had in that case, right? So be careful. This is constant. And yeah, a very amazing example of how we can use divide and conquer with recursion in our favor, and always after some constant number of steps, which in this case is at most 2, sometimes 1, sometimes 2, we basically end up with a sub-problem which is half as difficult or as complex as the previous one, which helps a lot because we get really fast to the simplest problem for which we have the stopping point, and that's it. Alright guys, have fun coding and I'll see you on the next one.